Hello everybody, so we're starting on the next section about the ideal gas law, which is in actually chapter 15. We're skipping 14 for the moment, we'll go back to it later. The first part of the slides for this lecture are chapter 12, and that's what we covered, chapter 13. That's what we covered in the last series, okay? So, once again, you're going to print these notes. I did change the notes a little bit. You only have to print the last few slides. So you're going to look for the slide that begins where we left off, which is combined gas law. I think it's slide 17. Okay, so what we're going to do here is try to identify the pieces of information provided in the problem. This is a wordy one, so we're going to break it down. I'm going to highlight what I think is important as we go. So it says the zombie apocalypse has occurred, and I'm a respiratory therapist. Oh, so this is probably a gas problem because respiratory is all about gases. It was discovered that keeping a zombie on oxygen therapy relieves their need to eat brains. The oxygen pressure must be within the range of 0.85 to 1.15 atmospheres in order to keep them from eating my brain. Okay, so I guess respiratory therapy has become a really important job. And then it says, my zombie ward currently has an oxygen pressure of 0.95. Okay, that's great because that is definitely in the range to keep everybody from getting brains eaten. And it says the temperature is room temperature. Okay. So it says room temperature, which is, about 20 degrees Celsius. So I'm going to just jot that down. And, okay. So and the volume of each gas mask that we have is 2.5 liters. Oh, I guess we must be having gas masks. Okay. So the power goes out and the furnace stops working. So the temperature goes to 15 degrees. So it went down. So if the temperature goes down, so temperature went down, I would expect, let's see, pressure. Well, let's say, when we know from Charles' law that if the temperature goes down, then the volume also goes down. So like when he put the balloons in the liquid nitrogen, they shrank. So that's colder, and so it shrank. We also know that when volume is decreasing, pressure goes up if the same moles of gas is there. Okay. So the backup generator kicks on to pump oxygen, but it's pumping too fast. The gas inflate to 3 liters. Oh, now we have a different problem. Okay. The gases actually are inflating. We thought the volume would go down because it got colder, but they're inflating to 3 liters. So we need to find out what the new pressure is. And I guess if it's over this 1.15, then the zombies are going to eat our heads. Our brains, rather. Okay. So.
Siri.
Okay. So the combined gas law has this form. It's P1V1 over T1 equals P2V2 over T2. So I like to establish what my various, variables are. So I'm going to call this P1 because it's atmosphere, so it's a pressure, and that's the first pressure I'm given, so I'm going to call it that. I'm going to call this one T1 for the same reasons. Temperature is Celsius, so. And then V1 must be liters there. Okay, so then I keep going, and I'm going to do P2. I'm not sure. I guess we're trying to find P2, so that's P2. So that must mean 3 liters is V2, and the temperature 2 is 15. Okay, so on the next slide, we're just going to try to write those down. So P1 is 0.95 atmospheres, so P1 is, 0.95 ATM. V1 was 2.5 liters, and T1 is about 20 degrees Celsius. P2, oops, let's do this in the other color. P2 is unknown, we're trying to figure that out. V2 was 3 liters, and T2 is 15 degrees. Now, one thing to note is whenever we're doing gas problems, the very first thing to do is convert to Kelvin. So we do that by adding 273 to each temperature. And so you get 293 Kelvin initially. And here we go to let's see, I guess it would be 288 Kelvin. Okay, and then if I'm gonna solve for P2 in this equation, we should rearrange the equation to have P2 by itself. So if it's P1 V1 over T1 equals P2 V2. I find that this part is one of the hardest parts for people, so it's easier to rearrange it as variables than it is to plug it in. So most people prefer to do it that way. To keep from making any mistakes, I'm going to show you this time step by step how to do this. Generally, you want to kind of practice rearranging these equations because it's going to be necessary when you do the test. So here we go. First off, I'm trying to get P2 by itself, so I'm actually going to write that in a different color so I remember. That means that everything that's black needs to be on the same side of the line. So first I'm going to deal with this T2. It's on the bottom of the denominator, so I can't do anything unless I get rid of that. In order to get rid of it, I have to do the opposite, and I'm going to do it on both sides. So the opposite of division is to multiply. And when I do that, the T2s on the right-hand side cancel. So that means I'm multiplying by T2 on the left, so that's going to go on the top. These T's are not the same, so I cannot cancel them. They have to stay the way they are. Okay. And so on the right, that leaves P2 times V2. If I want to get P2 by itself, I have to do the opposite thing to V. So right now it's being multiplied, I'm going to divide. Okay, so I'm just going to clean this up, give myself a little bit of working space here. So our equation is P1 V1 T2 divided by T1 times V1. So it sounds complex, but it's really, it's a lot easier this way than trying to plug the numbers in and make it work out. Okay, so to solve P2, I'm just going to substitute the variables that I already know. So we said P1 is 0.95 atmospheres. V1 is 2.5 liters. And T1 is 293K. And then all of that is divided by T1, which we said is 288K, times V2, which we said was 3 liters. It's right here. Okay, so before we do anything else, no calculator yet, so put it down. You probably already grabbed it, but put it down anyway. We're gonna check our units. If I'm trying to calculate a pressure, then it needs to be a pressure unit like torr or atmospheres, pascals. So we're going to cancel everything that's the same on the top and the bottom, and we do get atmospheres. So we have rearranged our equation correctly. If you get to this phase and you find out that you don't get atmospheres and you're expecting a pressure, then you did this rearrangement incorrectly. So go back and try it again. Okay, so alrighty, so we enter 0.95 times 2.5 times 2.93, so the top there, and we get 695.9 atmospheres. And then we divide that by the bottom, which is 288 times 3 on the bottom. So I use parentheses in my calculator. And so the pressure is 805,410. It keeps going, right? So this is not a whole number. I want to go back to my original data, so up here, where I wrote my original information. And I see that I have two significant figures, pretty much most of the time, 2 or 3. So that means that I can only keep 2. So my final answer is 0.81 atmospheres. And so we got to go look. Our range here was 0.85 to 1.15 atmospheres. And it's 0.81 atmospheres, so that's a problem. I need to heat up the masks quickly before the zombies escape and chew on my head. Okay. So the basic premise here is first, identify your variables. Second, rearrange your equation. And then third, plug it in. Make sure that the units cancel before you actually plug it into your calculator. So there we go. The next law, so we've learned Charles' law and Boyle's law. The next one was actually sort of discovered by Avogadro, which is the same guy that we named a mole after. And basically this was a competition between him and another scientist named Gay-Lussac. And Gay-Lussac wanted to hold the world record for the highest altitude ever achieved. And he actually did for about 30 years until airplanes were invented. And the reason he could do that was because he learned how to change and manipulate the proportion of gases to get the right density and get the balloon to go higher. So he learned that any particular temperature, at any given temperature and pressure, the amount of gases that reacts is very predictable. So if I take 1 liter of carbon gas, and 2 liters of oxygen, you're always going to get CO2 gas. Or if I take a better example, since carbon gas isn't actually a real thing at atmospheric pressure. If I take 1 liter of oxygen gas and 2 liters of hydrogen gas, I'll always get a perfect amount of water. It's water in the gas phase, actually. That particular reaction doesn't work for making air balloons because it's explosive. It's a big explosion. So that one wouldn't have worked in his balloon, but it's the right idea to get him able to go up higher and higher and higher. The interesting thing about it is that this ratio between volumes is always a whole number. So like 1 liter of oxygen for 2 liters of hydrogen. What this led to is the discovery that if you have 2 gases, even if they're different elements or compounds, at the same pressure and temperature, then they have the same volume, which means they also have the same number of moles in that particular space. As it turns out, under standard conditions, so again, just a reminder, that's 0 degrees Celsius, 1 atmosphere of pressure. STP again means 0 Celsius, 1 atmosphere of pressure, and 1 mole of gas. Under those conditions, every single gas, no matter what it is, always has 22.4 liters as its volume. So this is a handy fact. You can turn it into a conversion factor that relates moles of gas to the volume. So if I know the volume of a gas, I can figure out the moles as long as it's under standard conditions. Okay, so the 3 laws we have are outlined here. So Charles' law relates volume and temperature, and it says that they're proportional. This little sign means proportional. Boyle's law says they're inversely proportional, so we take 1 over P on the right. And Avogadro's law says it's proportional to N, which is the number of moles.